Hello, discrete math fans. Now let's show how induction can be used to compute integrals. Oh no, integrals. Alright, don't panic. I'm not going to make you remember a bunch of details about how to evaluate integrals, especially improper integrals. But look, everybody in this class has taken freshman calculus, so I'm going to feel free to go ahead and walk through the calculations. You've seen all of this stuff before. I don't want to have to explain details like how do you evaluate integrals, how do you do integration by parts. I'm going to assume that you know all of this, or at least you've seen it before, because I know you have seen it before. But don't feel like you need to go brush up on your calculus. So here's the problem that we want to do. Let's evaluate the integral from 0 to infinity of x to the n e to the minus x dx. And we're going to show that that's equal to n factorial for all n in the whole numbers. Now this is kind of interesting to show that you've got an integral that ends up giving you something that is just an integer product. It's a little bit unusual to run into things like this. Now if you're interested in learning more about this particular integral, I would suggest that you go look up something called the gamma function, which is directly related to what we're doing here. I'm not going to talk about the gamma function. This could be something that you might be interested on your own. All right, so let's let P of n be the predicate that's up here. So this equality here. Now, in order to show that P of 0 is true, we have to show that the integral from 0 to infinity of e to the minus x dx is equal to 0 factorial, which is 1. What happened to the x to the n? Well, we're using n equals 0, so that's going to be gone. All right, so when we evaluate an improper integral, we always have to rewrite it as a limit. That's just what you have to do. So we rewrite it as a limit as b goes to infinity of the integral from 0 to b of e to the minus x dx. That's an easy antiderivative. It's just negative e to the minus x. If we plug in the b and the 0, then we'll get this expression here. And then we'll end up with a 1 because as b goes to infinity, this piece here goes off to 0. And then we'll just be left with e to the 0, and that's 1. Therefore, P of 0 is true, and that's our basis step. Now let's let n be an element of the whole numbers and assume that P of n is true. So that is, we're going to assume that the integral from 0 to infinity of x to the n e to the minus x dx is equal to n factorial. Remember, n is an arbitrary but particular value of n. Now we're going to try to prove that P of n plus 1 is true. That is, we want to prove that the same integral but with an n plus 1 in the exponent there gives us n plus 1 factorial. And again, as is the case with all sorts of induction problems, we want to leverage what we know, which is this. We have assumed that to be true. All right, the method of integration is to use integration by parts. All right, as usual, we rewrite our improper integral as a limit. And now we'll talk about the selection of u and dv for integration by parts. All right, I think this is the proper selection here. We're going to let u be equal to x to the n plus 1, and then dv is equal to e to the minus x dx. And if you compute du and v, you'll get these quantities here. The choice of u and dv is driven by something called the detail rule. If you really want to know all about this, go back and look at the videos that I have for Calculus 2. All right, so the integration by parts formula tells us that we should get uv. So here's uv, and that ends up going here. And then we have v du, and that's what goes in here. And now when we plug in the b and the 0 for the first term, so this guy right here, we end up getting this. We'll talk about that in a moment. And then we can spread this limit to both terms here. And so let's talk about each limit separately. Now the evaluation of the first limit, I'm going to save that for homework. It's not a particularly difficult calculation. It can be done using L'Hopital's rule together with induction. And it turns out that that limit's going to end up being 0. And you're going to show this on the homework. It's not a difficult calculation. All right, now let's talk about the second limit. Now let's take that limit and rewrite it back as an improper integral. And then we'll just factor out the n plus 1. Now, what's left over? Well, if you'll remember, this guy right here was the original integral that we started with, and we have an induction hypothesis about that. Our induction hypothesis is that this integral here is equal to n factorial. Notice that we've put the star above the equal sign to indicate that we are using the inductive hypothesis. And then n plus 1 multiplied by n factorial is just equal to n plus 1 factorial. So as usual, I can say, therefore, p of n plus 1 is true. And so by the principle of mathematical induction, p of n is true for all n in the whole numbers. Keep in mind that I swept under the rug a limit calculation in there. That's something that you're going to complete on a homework assignment so that we have a complete proof here. Okay, that's all for now.